In this video we're going to demonstrate how phasor diagrams, or showing the phasors in the complex plane, can demonstrate the relative phases and magnitudes of voltages and currents within a circuit. To do this, we're going to remind ourselves that phasor V is equal to phasor I times the impedance. Now, for example, in a resistor, the impedance is R, and V then is simply equal to I times R. R is a real number, so there is no phase term associated with the impedance of the resistor. And we say that the voltage is in phase with the current in a resistor. So if we have, just arbitrarily choose the current to have a zero phase angle, then the phasor voltage associated with the resistor, or the voltage across the resistor, call it V sub R, will have the same angle as I, be in the same direction, but just have a different magnitude than I. And in fact, the magnitude of this will be R times I. Alrighty, unlike in a resistor, a capacitor introduces a phase difference. We know that V across the capacitor is equal to I times Z. Well, the impedance of a capacitor is 1 over J omega C. We'll bring that J up into the numerator with a minus sign, and we'll have then this is equal to I times a negative J over omega C. Well, that negative J term is the same thing in that negative J in rectangular coordinates is the same thing as a minus 90 degree phase term in polar coordinates, where we have then that V is equal to I times 1 over omega C times e to the minus j 90. So whatever the phase of the current is, when we multiply the current times the impedance, there's a negative 90 degree phase term that gets added to the current. And so once again, if we let the current have a zero reference angle, then the voltage in the capacitor is going to be 90 degrees less than the phase of the current, or we say that it is 90 degrees, the voltage is 90 degrees behind the current, or we can say that the current is 90 degrees ahead of the voltage. Finally, we look at the voltage across the inductor, and we have phasor V sub L, and of course these are all phasor terms over here. Phasor V sub L is equal to I times Z. Well, the Z, the impedance of an inductor, is J omega L, which is equal to I times omega L times J. Well, J is the same thing as e to the positive J 90. And so in an inductor, the voltage will be 90 degrees ahead of the phase of the current. Whatever the phase of the current is, when it gets multiplied by the impedance of the inductor, which has this positive 90 phase term with it, that positive 90 gets added to the phase of the current, and the voltage will be 90 degrees ahead of the current. So over here we had that being I. Once again, we'll reference I, just arbitrarily choosing it to have a zero phase. I, then V sub L will be 90 degrees ahead of phasor I. So we say that the current lags the voltage in an inductor, or the voltage leads the current in an inductor. Notice that the voltages of the capacitor and the inductor are 180 degrees out of phase with each other. The voltage of the current is the voltage of the capacitor lags by 90 degrees. The voltage of the inductor leads the current by 90 degrees. There's a mnemonic that goes along with this that dates clear back to the late 1800s, when much of electrical work that was being done was associated with refrigeration and creating ice. And the mnemonic is Eli, the Iceman. What this is suggesting is that E represents voltage. As in physics, we talk about the EMF. So E is voltage, I is current, L is an inductor. So in an inductor, the voltage leads the current by 90 degrees. In an inductor, the voltage leads the current by 90 degrees. In a capacitor, the current leads the voltage by 90 degrees. So in a capacitor, C, the current is 90 degrees ahead. So as in the word ice, I comes ahead of E. So I is leading the voltage over here. In Eli, the voltage is leading the current. Now let's demonstrate how these phasor diagrams can be used to demonstrate the various or the relative phases of different voltages and currents within a circuit. Here we have a single loop circuit, and writing 1 kVL, we know then that V sub S, phasor V sub S, is equal to I times, well, first of all, V sub S, just summing the voltages, is equal to V sub R plus V sub C plus V sub L. And of course, these are all phasor voltages. Now let's go ahead and put in that V sub R is equal to I times R. In this case, R is 8 ohms. Plus the voltage across the capacitor is just going to be I times Z sub C, which is I times a negative J8. Plus the voltage across the inductor, it's a J2 ohm inductor, so the voltage across that will be I times J2. So we have three terms here, three different phasors. These are phasor voltages equal to 8I minus J8I and positive J2I. Showing this explicitly with the phases, this will be I times 8. There is no phase difference between the voltage across the resistor and the current. On the other hand, we have I times 8 times e to the minus j90 in the capacitor, plus I times 2 times e to the positive j90 for the inductor. So again, what this is saying is that the voltage across the inductor is 90 degrees greater, or let me say it this way, the phase of the voltage across the inductor is 90 degrees greater than the phase of the current. On the other hand, the phase of the voltage across the capacitor is 90 degrees behind the phase of the current. So let's just start out and say that this is the current. We'll say that it has a magnitude I0. The voltage across the resistor is 8 times that, or V sub R is equal to 8 times I0 in length, and it has the same angle as I. The capacitor, on the other hand, is 90 degrees behind the current, so the voltage, V sub C, is 90 degrees behind the current, V sub C, and it's down here at negative 8 I0. And the voltage, let's see, that's the voltage of the capacitor, and the voltage of the inductor is 90 degrees ahead of V sub L is equal to, the length of it is equal to 2 times I0, and it is at an angle 90 degrees ahead of the current. So our three voltages, the voltage across the resistor is in phase with the current, the capacitor is 90 degrees behind the current, and the inductor voltage is 90 degrees ahead. Now we have here that V sub s, the source voltage, is equal to the sum of those three terms. So when adding phasors, you do it just like you do vectors, and that is tip to tail them. Here's V sub r. Add in V sub c. That comes down here like that. And then add in V sub l. That brings us back 2 units back that way to this point here at negative 6I0. And so we end up at that point, and that is V sub s then. Let's see how good of a job I can do drawing a vector down there. Not very good. That's a straight line vector. That's better, I guess. So V sub s then is equal to V sub r plus V sub c plus V sub l. This resultant phasor is V sub s. What does it tell us? Well, it tells us that V sub s is something less than 90 degrees behind the current, or that the current in this circuit I is leading the voltage source by some angle less than 90 degrees. It also tells us the relative length of this voltage is longer than V sub r. It's shorter than V sub c, because V sub c and V sub l are opposites. I guess to be more accurate, it would be to say that V sub c and V sub l are in opposite directions, and they tend to cancel each other. Let me say that one more time, just a little bit differently, and see if I can make it a little more clear. V sub s, the source voltage, is equal to the phasor sum of V sub l plus V sub r plus V sub c. By diagramming or drawing in V sub l, V sub r, and V sub c, and then adding them tip to tail, we can see the relative length and phase of the source to the voltage across the resistor, which is in phase with the current, the relative length and the relative angle of the source relative to the voltage across the inductor, and the relative length and relative phase of the source relative to the voltage across the capacitor. Again, this doesn't give us a real accurate, but it does give us some feel for the relative phases, the phases of one of each of these voltages relative to the current and relative to the source.